okay, we now have a bunch of dt/dt's. We have this, say, vector, again, of dt/dt's equal to the number of nodes in our solution, right, in our domain. So the next thing is we need to figure out how to move forward in time. Well, it's just as easy now as taking the same approaches we use for 0D problems and applying them here. So we discretize our domain, our time domain, into some number of time steps, and we just step from one to the other through time, right? So to discretize time, again, that would be Tj, our jth time is just equal to, we'll use the index j minus 1 over m minus 1 times tsim, tsim being the amount of time we're simulating. That's true for j equals 1 to m. M is the number of steps in time. Our delta t is then tsim divided by m minus 1. Okay. So now the tricky part is it's kind of like the 2D numerical problems that we did, where the tricky part is really just the bookkeeping part, the getting the indices right. Okay, so what we're going to do is we're going to say, I'm going to introduce this variable t, right, ti comma j. So I is going to correspond to my position x. J is going to correspond to my time t. Okay. You could do this, you could do it either way, right? I think always do it this way, where the spatial node comes first and then time comes second. And mostly that's just because it's easier to plot things in the end if they're in that order. But you could do it either way, right? Just make sure that when you're doing this, that you keep track. I is my space node, j is my time node, and don't flip them around, right? It's really easy to mess that up. So the other thing we want to figure out is the initial condition. Right? So we have initial condition. So my initial condition is going to be t infinity, right? Everything's at t infinity. So how do I actually implement that initial condition for this problem? Well, I need every single node in space to be at t infinity. Okay, so I would have to write in EES or in whatever program, I would have to say ti at time step 1. So ti at time step 1 is equal to t infinity. And I'd have to do that for I equals 1 to n. Let's see. Yeah, because n is our number of nodes, right? So we're saying for every single node, I have to go through and set this. Okay, so you can't just set one temperature, you have to do it for every single node. Right? And you can see now this would be pretty easy to change if you have a different initial condition. Let's say something more complicated. Let's say you ran your first simulation for phase A of your problem. You came up with a solution. You then wanted to implement that in your transient model. You just take your solution from your first phase of what you're doing and copy the temperatures over, and that could be your starting point. Right? You could have any function you want to be your initial condition because the numerical technique doesn't really care. You just set the value and move on, right? So in that way, the numerical models are obviously much more flexible than an analytical solution where you have to have the boundary condition, the initial condition is part of the analytical solution. Here, you can really do anything you want once you have this. Okay, so here's our initial condition. Here's kind of everything discretized. So what do we do next? Next, we will start off with the simplest technique, right? Euler technique was where, if you remember in our transient problems, we said, if I want to predict the temperature at some time step j plus 1, my next time step, all I need to do is take my current temperature, Tij, and add to that the derivative that I computed, my state equation, times the time step. And I think the critical part here is we're doing what? We're evaluating this derivative at the temperature Ij and at time j, right? The beginning of the time step. So this makes it really easy to implement. We have the state equations, we compute them at that moment in time, everything's explicit. And once you have that, you can then just take your step. But again, if you remember, this was kind of the worst method because it's unstable, it's first order. And so you kind of end up having to take a lot of time steps in order to get it to be accurate. But okay, anyways, let's start with this. These are the equations up here that we just solved for. I didn't explicitly solve for these two, but you could figure that out yourself. So what we want to do is start by taking the first time step. Okay, so this is just as a kind of a way to make systematic your approach. You always want to start with the first time step, take one step, and then substitute back, j for 2, or j plus 1 for 2, j for 1, and so on. So we'll start with the first time step, and then we'll extend it from there. Okay, so if we do this, it's pretty straightforward for Euler. Probably should have just printed this out, but for Euler, we would say T1. So remember, 1 is our spatial node. So T1 time 2 is going to be equal to, what's up here, Tij. So that's T node 1 time 1, T11. Remember space and time, plus the evaluation of this derivative, right? So this would be, do I need to write all this out? So this would be this entire thing here, right? Put that here, times my time step, delta t, right? The thing you want to be careful about is, sorry, this will be a little painful. Let me just do it this one time. So I want to make sure you get the indices right. So let's write it out. Okay, so we have this entire quantity, which is 2 alpha over delta x squared times t. So let's be careful with the indices, right? So T2, what does T2 mean? T2 is our space node 2. Okay, so we want our space node 2 at time what? At time what's being evaluated for the Euler step? At time Tj. So that's at time 1, right? Minus T space node 1 time 1. Okay, plus h bar perimeter over AC rho C, T infinity, which isn't changing, minus T space node 1 at time 1, plus what's left, 2 q dot over AC rho C delta x. Delta x. Okay, so all of that is then times our time step delta t, our full time step. Okay, so that's just the part to pay attention to is getting the indexing right. Okay. So then let's see, that was for node 1, 2. So then for node I2, we want to do the same thing, Ti1. So it's basically the same, so I'll just write it quickly, but it's going to be this quantity, alpha over delta x squared, and then times T space node I minus 1, plus Ti plus 1, space node Ti plus 1, time node 1, minus 2 Ti1, plus h bar perimeter over AC rho C, T infinity minus Ti1, okay, times delta t, and that's for I equals 2 to n minus 1. Okay, so just a lot of writing there, but again, pay attention to the index and note that now we have the I minus 1 and I plus 1 appearing. So I think I have a pretty good picture. You can do the same thing. I won't do it, but for T n2 is just going to be T n1 plus the evaluation. Right? So now we have our set of equations that captures how we move from time step to time step. This is for the Euler step, right? This is for one evaluation of the derivative at the beginning of the time step, and we then move forward. So let's look at how this is implemented in EES. So first we'll go into EES. This is, I think, the same thing. So we first we discretize our domain. Right? So here's our X domain. We have, I guess, taken 6 space nodes and 21 time steps, and then we discretize our time domain here. And then we have to specify our initial condition. Right? So here, for every space node I at time 1, that's going to be equal to T infinity. Right? And again, if you want to make this something more complicated, you just replace this with some function of space. Right? So then the first thing we're doing is we're going to take our first step. We're doing this for a space node here, time index here, and we do it for every single space, right? And so you just implement exactly what we did. This should be the same thing, right? And why do we do this? It just makes it easier to debug. So if you figure out that you're missing an equation here, then it just shows up as missing one equation. If you try to do everything all at once, it shows up as missing m equations or m times n equations. So it's a little bit harder to debug it, right? So this is just the way to solve it. So we can solve it. We can look and we can see, all right, I'm trying to go from time 1 to time 2. And here's the step for each of the space nodes. And you can see, yeah, it looks like it's pretty much working, right? Okay, so once we do that, then you can go back and comment out this stuff that is just the first node. And then we implement our Euler step for everything, right? So this would be for everything, and we can solve it there. Hopefully this solves. Yeah. Okay, so now we can see, if you sort this, we can see for every single space node, which we said there were 6 of them, this is how the temperature is moving through time. Right? And we should have, what, 21 of these steps? Yeah. Right, so that's how that's basically how you do it. So once you understand the Euler technique, then it's pretty easy to go back and do some of the more sophisticated techniques, which we'll talk more about those next time. Right, so, okay, so that's, so that's that approach. So we talked about that. I guess we could show you how to do this in MATLAB too. I mean, it's pretty straightforward. Let's look at that. So here we have the same problem. Setting it up, we discretize, let's see, it looks like we're discretizing now 21 steps in space, right? So 21 steps in space, and then in time we have 500 something steps. Go through and specify our initial condition, doing that here, and then we're taking this step, right? So we can look at this, and if we actually run it and plot it out, we will see. So this is now as a function of time. Right? These are the temperatures at our different spatial nodes. So the top line must be at the base of the fin, right, where you're forcing the heat in. And then as you go out in the fin, you kind of move down in the line.